Hi there guys, this is 12F now. We're talking about exact solutions of coupled differential equations. Now we've dealt with differential equations before where we had things like dy dx is equal to x times by y. So the difference is now we're talking about finding dx dt and dy dt. So we're talking about differentiating with respect to time. We're talking about growth models and what's happening to our xy coordinate points over time. Okay, now these ones are also potentially linked. So when we write dx dt, that could be a function in terms of x and a function in terms of y combined. So say, for example, dx dt could be equal to 2x plus 3y. Now, these are also first order differential equations because we're not dealing with any higher powers than just x to the power of 1 and y to the power of 1 here as well. So this will become apparent as we go through the exercise, of course, but let's have a look at this just brief introductory question here. They say two fungi, X and Y, are growing on a tree. X is the faster growing fungus, but when it encounters Y, Y will dominate and benefit from the nutrients in X. So their growth over time are dependent on each other. So we're going to have dx dt or dy dt as both a function of x and also a function of the size of y, size of x, size of y. So when they encounter each other, then their growth is going to change. Okay, now there is an investigation which continues here, this investigation 4, which is really quite involved. And I will go through that towards the end, but it leads to this. And this, fortunately, is given to you in the formula booklet. So let's look at the formula booklet. It's the absolute last thing on the final page of your booklet here. And it says exact solutions for coupled linear differential equations. And you'll see here you've got x, which is your xy coordinate point, essentially. Okay, so that's a vector x. The vector x equals xy. And it gives us here pretty complicated formula, and the lambda 1 and the lambda 2 there, which you see in there, are eigenvalues in this, and the p1 and the p2, which are vectors, are the associated eigenvectors. It doesn't say that in the formula booklet. It doesn't say that here as well, but it does show you that through the investigation from before, which I will do at the end of this example here. Okay, and then it says where a and b are real numbers depending on the initial condition. So in fact, those will depend on the eigenvectors which you will choose. Okay, and it will depend on the initial conditions. In other words, when x is this, y is this, and t at a particular given time. Okay, so for example, commonly they'd say when time is 0, here's your xy coordinate point. So that would be your initial conditions. Okay, so there's a lot to take on board. There was another pink box up here on the previous page which said, just to describe what a system is again. So it says a coupled system is one in which either the equation for the derivative of x contains a function of y, or the equation for the derivative of y contains a function of x, or both of these. Okay, so yeah, so that's what it's talking about. Now let's have a look at doing this question, example 5. The process of this is essentially what you need to learn. From my point of view, I would want to know as well why this is true. And again, I'll talk about why it's true afterwards. Okay, so here we go. And I've copied this bit here. Here's your eigenvectors. Here's your eigenvalues there, the lambda 1, the lambda 2. This is the setup here. Of course, that's exactly the same as how we made eigenvalues in the first place. We said our matrix A applied to the vector x, which of course is an xy vector, that's x and y there really in the vector, is equal to your eigenvalue times by x. Okay, and remember from before that we also said that that's your matrix A, take away lambda I and in our case, we're dealing with this in 2 dimensions. So we're taking our identity matrix, and that's applied to X is equal to the 0 vector. So that is going to be pretty useful. That is how we're going to find out essentially what our 2 eigenvalues and eigenvectors are here. Now, for us, we're going to need to identify what the matrix is to start off with. And you can see, of course, that coupled system is this. So we're going to need to identify this. That's going to be this. And then we're going to move on to this. So we're going to take this, take it to lambda x. Okay, so practically, let's deal with this. So we've got x dot y. Oh, you probably need to know what x dot means. X dot means dx dt. So that's just your derivative with respect to time. So you can put x dot there just to say this is a quick way of writing our derivative. And you could define that to be in terms of y instead, but in this case, we're clearly doing it in terms of time, because they're talking about time as the additional parameter here. Okay, so there's our 2 derivatives there, and of course y dot means dy dt as well. Okay, so this is equal to this, and that's essentially in matrix form is going to give us 3 and minus 4 and 1 and minus 2 of x, y. Okay, so that's going to give us out the two terms here. So if we times these by these, we'll get out the answer for this. So we've just put it in a vector and matrix form. Okay, so now we've got this essentially, that's this. So our matrix, the M, is this thing here. So now in order to solve for our eigenvectors, we're going to need to do this thing here. And so that's going to give us, let's just do it up to the top here. So now we've got 3 minus lambda and minus 2 minus lambda. We've got the minus 4 there and the 1 there. And we need to take the determinant of that. And often in the book, they just get rid of the brackets, of course, when they do that. And they say the determinant of that is equal to 0. This is just the process which we went through from before when we're talking about this matrix being singular and looking for solutions. Okay, so we've got this times minus, just take that minus out to the front. We've got 2 plus lambda there. And then we've got minus these 2 times together. So that's plus 4 is equal to 0. And so that's going to give us minus, and we've got minus lambda squared. And then the 3 times the 2 is going to give us 6 in there. And then, of course, we've got minus 2 lambda and 3 lambda there. So that's giving us plus lambda plus 6 and plus 4 equals 0. And that's going to give us lambda squared minus lambda, and that's going to give us minus 2 there equals to 0. So the 2 solutions are from factorization. So we've got lambda, take away 2, we've got lambda plus 1 there equals to 0, and that gives us lambda is equal to 2, and also lambda is equal to minus 1. So we're just going to call that lambda 1 is equal to 2 and lambda 2 is equal to minus 1 there. Let me just check. That's how the book does it as well, just to be consistent with that. Yeah, they're going with 2 as the first one here, I can see. Okay, but you can do it the other way around, of course. So we've got the eigenvalues. We now need the eigenvectors. And the eigenvectors are essentially putting this back into here, this matrix here, and then applying it to x to get 0. So when we put 2 in, let's go to here, and then let's go around over here. So when we put 2 in, we're going to get the matrix 1 from here, and then minus 4, 1, and then again minus 4 when we put 2 in there, so minus 4. We're applying that to x, y to give us 0, 0. That gives us out, obviously, the equation x minus 4y equals 0 twice, which gives us out the equation y equals to quarter x. So the eigenvalue that we could take could be potentially 1 and a quarter, but it's better to deal with whole numbers. So let's just times all of that by 4. It's going to be 4 and 1. So there we go. We can see there's an example of an example there. So that's just an example of an eigenvector which works in that case. Now the second one, so that was when lambda was equal to 2. Okay, now let's look at when lambda is equal to minus 1. Okay, so when we put minus 1 into here, we're going to get out the vector for the matrix 4, minus 4, and 1, minus 1 there, by 2x, y gives us 0, 0. And this leads to 4x minus 4y, 4x minus 4y is equal to 0, which leads to, or you know, likewise from the bottom, x minus y, which leads to x equals y, which leads to, let's just squeeze this one in here, the vector 1, 1. Okay, so that's again an example of this one here. So that's our other eigenvector. Ooh, okay, so what have we done so far? We've found the eigenvectors, the eigenvalues, sorry. We found the eigenvectors. And now we just need to find A and B. Okay, so let's set this one up. So we've now got x. This is a vector, so I've put the underline there. We've got A, that's not a matrix. It's not the same as this matrix here. That's just a constant. We've got B to the 2t. And then we've got 4, 1 there. And we've got plus B, e to the minus t. So let's just bring in the other eigenvalue of minus 1. And then we've got the eigenvector associated with that is 1, 1. Now, obviously, I could have chosen 2, 2 there, but that would have just changed B to be half as much. So these constants here will vary according to the eigenvectors which you go for. But obviously, it's easier to go for the simplest combination of numbers that you can, and whole numbers and positive if you can as well. So there you go. That's done, but we've got some initial conditions. What are the initial conditions? They're saying that we have when x is 4, y is minus 2, and t is 0. So when t is 0, this is just going to become 1. So we'll end up getting out x is 4, so we can put 4 in there. Remember, this is xy vector. Got minus 2 there, and that's giving us a lots of this. So let's put 4a and just a in there, and that's plus b. Again, that becomes 1 when we put t is equal to 0 in, so we're just getting plus b. Now we've got a set of simultaneous equations to solve there. This one, 4 equals 4a plus b, and minus 2 equals a plus b as well. So this gives us a is equal to 2, and b is equal to minus 4. You can put those into your calculator and solve, just to speed things up. So we've got a is equal to 2 and b is equal to minus 4. And so obviously we can now put those things into here, and that will give us the final solution for x. Okay, so that's what we've finally done, just saving a bit of space there. Okay, so there's the solution. That's done. That's the mechanics of this kind of problem. That's the technique. Now, in terms of part B, it says determine the long-term ratio of x to y. Well, for that, you need to think about what happens to this. Let's just highlight this. So when we're talking about determine the long-term ratio, we need to consider these two functions here. So what happens when you take t to infinity? with those two functions? Well, you can see that this is going to get pretty large, and this is going to get extremely small. So e to the power of minus 100 is the same as 1 over e to the power of 100. So this is going to tend to 0, and this is just going to tend to a large number. But whatever that large number is there, this is essentially just a large constant. So this will entirely disappear as t tends to infinity, and this will just be a large constant in front of 4 and 1 there. So in front of the x is 4 and the y is 1. But whatever this constant is, we'll still have the same ratio of x to y. It will be from here. This will just completely disappear. So the ratio that we're going to get is the ratio of the 4 to 1 there. So it's x, y will be in the ratio of 4 to 1. Because we're just timesing this vector here, this eigenvector, by some large constant. Okay, so there's the long-term vector. Now let's just have a look at how they do that in the book as well. They have not put much explanation to this at all. They have just said the second term tends to 0 as t increases. Fair enough. Okay, so now here's the long bit. Okay, so now if you want to get on with the questions and you think I'm just going to roll with this, then that is fine. However, there is a fair bit of explanation to investigation 4, and I'm basically going to take you through 1 to 4, and 1 to 4 will lead you down to this final solution here, which is what we want. And then after that, there's actually another investigation here, or another question, which is worth doing. But again, I'm not going to go through that one. I'm just going to go up to 4. Now, that doesn't seem much, but there's quite a lot in this. So hopefully you are sitting comfortably, or otherwise you can get on with the exercise now. So let's take this investigation. Give me a moment. And let's take 1 and 2 to start off with. And so investigation 4. And let's just solve these two to start off with. Okay, so 1 and 2. So it says solve the differential equation here. So this is just normal solving of differential equations. So we've got dx dt is equal to 2x. So we can split up our variables here if we integrate both sides. So we can do 1 over x dx integrated, and 2 dt if we integrate it as well. All we've done is we've split this up, and we've split this up by cancelling by both sides by this and dividing both sides by x, and then integrating both sides. That is the technique of solving differential equations, which we learned from before. So now this is log of x, and this is lambda t. What am I saying? Lambda t. This is 2t plus c. Okay, and if we take e to the power of both sides, we're getting our x is equal to e to the power of 2t plus c. But this can be split up into e to the 2t and e to the c. And of course, e to the c can be written as another constant. So I will put a e to the 2t there. That is pretty basic stuff. Okay, now we're also told when x is 5, t is 0. So putting in 5 there, putting in 0 there will give us 1. So a is equal to 5. So we're saying here that our x here, so this is x dot, but our x in this case, not x as a vector, just x, is going to give us 5e to the 2t. All right, that is coming from this. X dot is 2x. And so there we go. We're getting x is this. Now, similarly, when it says solve differential equations here, well, essentially they're saying, well, what is x, y? And you might notice here that rather annoyingly, they've said that now instead of x being 5, they've said x is equal to 3. But I'm going to continue with the kind of mistake which I think they've got here. So x previously would have been this, but now with this condition here, obviously if we changed x to 3 there, this would become 3 instead. So we get 3e to the 2t, still based on this, and the other one you'll get 5e to the 3t. Okay, so that's just coming out from this one here. So you could follow the same process for this one, and you clearly get 3t up here instead of 2, because this would have been 3 in the first place. Okay, so that's what we're going to get out for our solution for x and y. Okay, so that is done. Now let's look at the next bit. So the next bit says the vector x is often used to stand for the general vector of the variables, which is what we've talked about, which is xy, in which case they should have a capital X, bold X here, and x dot will be the derivative of the vector with respect to time. We've done that. For any system of equations that can be written in this format, and for which the eigenvalues of m are distinct, the solution is this thing here. Okay, so that's essentially what we talked about before. Towards the start of this exercise, that's the formula to our system of coupled differential equations. Okay, so for part 3, it says verify the system of equations in question 2 can be written like this. Okay, right. So let's take all of this chunk here now. So just copy this one across. So let's take this down to here. That's essentially what we're working on now. And from before, so from the previous part, let's also just say that we had from part 2, xy was equal to 3e to the 2, 3e to the 2t, and it was 5e to the 3t, 5e to the 3t there. Okay, so we're trying to verify that question 2 can be written in this format. Okay, so we have x dot, that's going to be equal to our x dot y dot, not as the vector, and we want to show that this is the same as m lots of x, y. Okay, so that's x dot, that's this thing here. That's m as a matrix, and that's x there, that's our coordinate point. Okay, so can we write it in this format here? So we're now thinking, again, go back to that previous bit, and we had x dot y dot. I just need to write this down as well. We had that based on 2x and 3y. So this thing here was actually equal to this, which is potentially a matrix applied to this thing here. So we need to say, well, what matrix is that? What's going to give us the 2x and the y when we apply that to x, y? Well, that's just going to be 2, 0, and 0, 3. This times by this gives us a 2x rather, and this times by this added together gives us the 3y. Okay, so there we go. So the matrix is this thing here. Now, so we verified that this can be written like this, and then it says find the eigenvalues and eigenvectors of m, and hence show that your solution can be written in this form here. Okay, so eigenvalues of m, we're going to need to do the technique for that now. So that's 3a done, by the way, there. So now 3b. So we're going to work out the eigenvalues. So we're going to do 2 minus lambda, 0, 0, and 3 minus lambda there. We want the determinant equal to 0. And in order to do that, we're going to times these two together, of course, and then take away these two. So that just turned out to be a really nice, easy quadratic, which we can solve. So you can see that 2 there and 3 there is going to solve those two things. So it's already factorized. So lambda 1 is equal to 2, and lambda 2 is equal to 3. Okay, so now we need our eigenvectors. So eigenvectors are put into here and then applied to x to give us 0, x the vector to give us 0. So to find the eigenvectors, we'll put in when lambda 1 equals to 2. Let's put it in there, and that becomes really straightforward. That's 0, 0, 0, and 1 applied to x, y equals 0, 0. So that gives us our y is equal to 0 there. And y is equal to 0 gives us the eigenvalue, eigenvector of y equals to 0 gives us the that's the essentially the x-axis. So x-axis can be anywhere along the x-axis. We can choose 1, 0 would be nice and easy. And then if we come up with the other one, when we've got lambda 2 equal to 3, then that gives us, again, when we put 3 in there, that gives us 0, and that gives us minus 1 there. So we've got minus 1, 0, 0, 0 applied to x, y gives us 0, 0. And that just gives us minus x equal to 0, or x is equal to 0. And that gives us the vector of 0, 1. Essentially, that's just the equation of the y-axis. Okay, so I've just picked any point along the y-axis. I've chosen 0, 1. Okay, so there's the two eigenvectors. So that's sorted. We've now solved to find the eigenvalues and the eigenvectors. Now we need to do this hence part. Okay, and so for the hence part, we need to show that your solution can be written like this. So let's take the solution. The solution was this. So we've now got x, y was equal to, we had 3e to the 2t and 5e to the 3t, but it's also equal to, supposedly it's equal to this. So we need to come up with this then. So we've got here, what's a going to be equal to? So we've got 3e to the 2t, so that's this thing here, multiplied by p1, so p1 is this thing here, so that's when the eigenvalue is 2. We've got this as our associated eigenvector, so that's 1, 0, and this could be this, just showing that's possible, so e to the 3t, and then associated with the 3, the answer there, we're getting 0, 1. Okay, so I've not solved to find out what 5 and 3 are. We've just shown that we can write it in this format here with some constants a and b, and it turns out the constants a and b are the same as these constants here from the original solutions. It can be written in those and stating the values of a and b. The value of a is 3 and the value of b is 5. Okay, so all we've done is verify that this is possible at this stage. So we've come up with a simple example. It was a really simple example, in fact, because it didn't have any y part involved in dx dt. So dx dt was only dependent on x, and dy dt was only dependent on y. So this was a really simple example here to illustrate this one. But yeah, you can see that our solutions from before, from question 2 essentially, have now been shown to be able to be put in this format at least. So we've just verified it in this situation to say that this is possible. And that's all we've done here. Now, for question 4, this is where it gets a bit more involved in terms of the general situation. It says, well, verify that this is a solution to this more generally by differentiating the right-hand side. So we're going to need to differentiate this and showing that it is equal to mx. So if we differentiate this, we get x dot. If we differentiate with respect to t, and what we're going to hope to get is that this is the same as mx. Okay, and we're using the fact that the matrix applied to the eigenvector is the same as the eigenvalue applied to the eigenvector. So that's just normal definition. So this thing here is simply a x equals lambda x. Okay, so that was just the start of eigenvalues and eigenvectors. That's the original definition. Okie dokie, so we're going to do question 4 now. So I'm going to take just question 4 on its own because I might need a little space for this one. We'll stop after this. So we're saying that we need to find x dot in this case, and x dot is going to be this differentiated and this differentiated. So this differentiated here is going to be, using the chain rule, that's lambda 1 a e to the lambda 1 t multiplied by b1. Okay, so that's our eigenvector in this case. So we've just, if our eigenvector there is 1, 1, then this will be the function inside both of those parts. But we need to essentially differentiate both of those parts when you've incorporated the function into the vector. And really, this is just a constant inside. So we can differentiate and then times by the constant in the x direction and in the y direction. We don't know what P1 is, but it's just a constant in the x and the y. So that is totally legitimate here. And then likewise for the next part, we'll do this for this one as well. And we're going to apply the chain rule in here. So we've got this and times by P2, so the second eigenvector. Okay, and at this stage, we can see that this and this into this is equal to your matrix. Now that, again, is just your straightforward initial definition as to how we found our eigenvalues and eigenvectors. So this and this I'm going to combine together to bring a constant here, of course. And so I'm going to put this one as a e to the lambda 1 t matrix applied to P1 and b e to the lambda 2 t and then matrix applied to P2. Okay, now you can see these are just constants, and we can use the distributive law for matrices here to bring out the m. So I can take the m to the front, a bit like when I say a b times c is equal to ab plus ac. That works with matrices. That's the distributive law doing here. So I'm taking the m to the front. We've got a e to the lambda 1 t p1 and b e to the lambda 2 t p2. Okay, and now you can see that this is just equal to x. Okay, therefore we have shown that this is equal to this, and therefore we have shown this is equal to this thing here, which is what they've asked us to, and provided that this is a solution. So that verify that this is a solution. Well, given that it's a solution, it does work. Okay, so not quite a proof, but given that it is a solution, then it does work. Okay, so we've done that. That is done. Okay, I think we can stop there. I think you'll be happy to stop there. Okay, so that is essentially giving us out this little statement here, of course. Okay, it says the coupled system x dot m is equal to the matrix times by x has this solution here. So it has this solution. It's not saying that's the only solution, although perhaps it is, but we have definitely verified that it is a solution, and that's what we've just put through here. That came together a little bit faster than I thought it did. Okay, guys, well, good luck with the exercise. I know this one is particularly challenging. Oh, and you would think, by the way, that that was sufficient in terms of the amount of work which we need to do in order to be able to access 12F, but in fact, there are phase portraits from B onwards here, and in question 2. So I'm going to do a separate video for phase portraits here. So there is an investigation about phase portraits, but again, I'm going to kind of skip over that a little bit, just talk about the results of that. Yeah, okay. Right, thanks for listening, and hope to see you back for the next one.